Hello everyone, it is time for another two-parter video. This is lessons 12 and 13 from Unit 2, so we're still in our polynomial unit. And this one brings in, finally, an operation that we have been avoiding for quite some time. And as you can see, that is division. I hope you're wearing your glasses for this, because it improves division. Anyway, okay, I'm smiling. Maybe you're smiling. I don't know. Okay, so in all seriousness, though, division is an operation that we have ignored up till now, kind of avoided. And the reason for it is because when you add two polynomials together or subtract them, like we did back in lesson 4, we still get polynomials. When we multiply two polynomials together, whether quadratics or higher, anything else distribution that we've done, you still get a polynomial. Division, not quite. Um, you can divide two polynomials, and if it works out evenly, great. But what if it doesn't? Then, well, it doesn't, and you do not get a polynomial. So let's set the stage here a little bit for how we're going to think about long division. Okay. So here's a few objectives. What we're actually going to learn here is how to actually divide one polynomial by another. And we can use that, we can calculate the result of polynomial division by using a diagram, or we can identify factors of polynomials using division. This last one is a pretty big one because with the factors, this tells you, of course, x-intercepts. So this can be useful to break factors off of polynomials that we otherwise don't have good factoring techniques for. And you'll see that a bit later on. Okay, it's also extremely useful to calculate leftover pieces if you happen to know one of the factors. Um, and that is another important usage here. So let's set the stage for how we're going to handle this. Let's start off with an easy problem. Let's say we wanted to do 30 divided by 6. What's 30 divided by 6? That's 5. And why is that? It's because 5 times 6 is equal to 30. Likewise, you could also say that 30 divided by 5 is equal to 6. Both of those are true because of the reason that I have provided. Um, so now, what happens though if it doesn't divide evenly? So let's say you had, trying to think of a good one here. Let's say we had 30 divided by 7 instead. Okay, so let's say you had 30. What's 30 divided by 7? Well, there's two ways that you can write this, right? How many times does 7 go into 30? It goes in 4, and there is 2 left over. 7 times 4 is 28, so that leaves 2 left over. So 4 remainder 2. This is the method that's preferred a lot by computer programmers because it keeps um, whole numbers around. Um, the algebraic way of thinking about it, 30 divided by 7 is equal to 4 and 2 sevenths. For the same reason, you have 7 goes into 34 times, and with a fraction of 2 out of 7. So that's how division works with numbers. So how does that connect to using algebra? So let's scroll down a bit, and then let's open up some new page. So what if we did the same thing, but we did it with x, right? So let's say you had x to the third divided by x. What's x to the third divided by x? X squared. And why? Because x times x squared is equal to x to the third. Likewise, we can also say that x to the third divided by x squared is just x. But what if I throw some extra numbers in there? What if I said x to the third plus 5 divided by x? Well, we know that x to the third is divisible by x, right? Because that's x squared. But this numerator is 5 units too high. Now, do we know what value of x this is? No, we don't. Um, if x were 5, then this division would work out evenly. Or if x, I think, were a lot of different multiples of 5, this would work. Um, but there's no guarantee that it does. We don't know what the value of x is, so we have to simplify this in the general case. And so we can say that we know that x to the third divided by x is x squared. But this 5, right, we don't know if it's divisible by x. And by the way, we're going to assume that x is not 0 here. So that would leave a remainder of 5 because we can't divide the 5 by x. We don't know. And, or you could say it in algebraic terms, it would be x squared plus 5 over x. And that actually is a little bit clearer here because you can divide each term separately by x. So that's kind of the way we're going to look at division here. But we have some processes in what to do when you have, you know, kind of larger terms, because when you get to things like, let's go one step farther. Let's say you had x to the third plus 3x squared minus 7 over x minus 4. Now we've got a big problem because the x doesn't divide evenly to all of these terms. Now you have two terms in the denominator. So how can you divide by these terms? Do you divide both terms, one term, and then you might have like terms somewhere along the lines? Do you end up with a 3/4 x squared and another x squared? It's a mess, right? So we need a process to figure out how to handle division like this, and then what we might actually get if it works out evenly, or if there's a remainder. So to kind of think about that, let's take a look at some examples of distribution. So let's look at this example here. So here's one. You can trust that this distribution works. X minus 3 times x plus 5 is equal to x squared plus 2x minus 15. Well, how do we know that that's true? Well, because we can distribute, right? X times x is x squared. X times 5 is 5x. X times minus 3 is minus 3x. And negative 3 times 5, negative 15. So we combine our like terms. Here's my like terms. And you get the x squared plus 2x minus 15. So one thing that is interesting to note here is that because this is true, and I want you to think back to the numbers that we used on the first page. 5 times 6 is 30, but likewise, 30 divided by 6 is 5. So it is also true that x squared plus 2x minus 15 divided by x minus 3 is going to be equal to x plus 5. But how in what, where, how is we're going to come up with that? That's the question. So this is true because um, the division is the opposite of multiplication. Likewise, the same thing is true if you have this expression. So here's a bit of a longer one. X minus 1 times x squared plus 3x minus 4. We've got an x to the third term. X times x squared is x to the third. Notice where my like terms are. I'm going to color code them. So the like terms are located along diagonals. And so you get a negative 4x and a negative 3x. It's a negative 7x. 3x squared minus x squared, 2x squared. Okay, that's the way distribution works. So now let's look at it from the reverse method. Since we know how the numbers get filled into the box, could we, if we know the expression that is the result of the multiplication, that is, we know the result of what goes into these boxes, could we reverse it to get what goes in the top row? Because if we could, then wouldn't that essentially be division? It is the reverse of multiplication after all. Let's give it a try. Let's look at the box here. We put x minus 2 on the left side because, well, it is x minus 2. Now, the top row we're going to leave blank. We want to know, what do we multiply x minus 2 by in order to get this? Now, at first, it may seem like a simple case of, oh, we'll figure out what multiplies to get to each term. But don't forget that in the middle, we have like terms. And we need to figure out what like terms exist in order to add to the proper numbers. Let's find out. Now, we have an x cubed, right? X times what gives you x to the third? X squared. So we know that this is going to fill in to be an x squared. Hey, so the first term is going to be x squared. And that makes sense because, again, x times x squared is x to the third. Now, what if we said, okay, what goes in this box here? Well, we know x squared is in the top, right? So minus 2x squared, negative 2 times x squared. Boom. Now, okay. Now, at first, it looks like that's all that we can fill in. But guess what? Remember, there are like terms here. And its like term has to be here. It's going to be diagonally up from the negative 2x squared. And this term is going to have to combine with the negative 2x squared, and it's going to have to equal the negative x squared. So negative 2x squared plus something is going to equal negative x squared. Well, what's that going to be? Negative 2 plus what gives you negative 1? 1. This is going to be x squared. Because now when you add those together, you're going to get a negative 1. Perfect. So if that's true, and we'll get rid of this now. Now we can look at what goes into the top box here. Since we know this now, x times what gives you x squared? That's got to be x. Okay, perfect. Now, x times negative 2. Negative 2x. Hey, it looks like we're doing it. All right. What else do we know? Okay, what else do we know? Okay, how about this 4? Okay, now we could do the same for this box, right? So you've got a negative 4x. So, but we already have a negative 2x. Negative 2x plus what gives you negative 4x? It looks like it's another negative 2x. Okay, and so those will combine to give you a negative 4x. So what goes up top? X times what gives you negative 2? That must be a negative 2. And now let's fill in the last box. What's negative 2 times negative 2? Positive 4. And if you notice, there is a positive 4 right here. So it looks like it matched. So could we have worked backward from the 4 instead to get that last one? Sure, we could have. But we went with the x's just in case. You could do it either way. But now what we get is x squared minus x minus 2. So it turns out that x minus 2 times x squared plus x minus 2 is equal to, well, I'm not going to rewrite it again. It's equal to that. So, get this. X to the third minus x squared minus 4x plus 4 divided by x squared plus x minus 2. Or sorry, or actually, that's the result. So, I mean, I guess it works either way, but just to make it clear, since we started with x minus 2, if we take this and divide by x minus 2, we get x squared plus x minus 2. Well, look at that. How amazing is that? We just actually performed division. Okay, so one thing that it's going to point out, it just worked. So when we did the negative 2x, the negative 2x, we got the negative 4x. We filled in the minus 2, and minus 2 times minus 2 is 4. The last number that we got just happened to match the 4. But notice that we just checked that it matched. Did it really have to match? No. And there's a case that it couldn't have. If this had been any other number, like a 17, it wouldn't have mattered. This still would have come out with a 4 in the diagram, but that's not 17. At that point, you'd have a remainder, just like the division that didn't work before. So in this particular case, we were lucky enough that this division worked out evenly, no remainder. But as you'll see, if those last numbers don't match, then you have a remainder. Okay. So now we're going to take that process, and what we just uncovered is really kind of the basis for division. And if you notice, it's got some similar properties to something that you did a while ago called line division. Okay, let's take a look at another example. Priya wants to sketch a graph of the polynomial f defined by x to the third plus 5x squared plus 2x minus 8. Okay, now here's the thing. Unlike the last bunch of units, right, when we were sketching graphs, we were sketching them based on factored form. And as we discovered, once you know what it looks like in factored form, you know the end behavior, you know the x-intercepts, and all of that. Here, we don't have that. So what do? Desmos? Nah. Let's see if we can find some factors. Okay. So the first thing that we need is we need some kind of starting point. Okay. So the first bit of information I'm going to tell you about this one is that f of 1 is equal to 0. And if you plug it in, you'll find that it's true. 1 plus 5 plus 2 is 8, minus 8 is 0. So it does work. So she suspects that x minus 1 could be a factor. How is that possible? Well, because if f of 1 is 0, then 1, 0 is on graph. Well, guess what? 1, 0 is an x-intercept. And so therefore 1 is an x-intercept. And if 1 is an x-intercept from our work that we did before, then we know that x minus 1 is a factor. So now my next question is going to be, are there more factors than that? So let's find out. In order to check this, And first, we're going to prove that this isn't actually true. And then the second thing is we're going to look to see if there are more factors. So let's actually go for it. Now, we're going to need a method, but we kind of know a method, right? So let's start to see if we can do it with the box method. Okay, so we're going to use what we have here. X minus 1 times this is equal to this. So to do that, let's draw a box. Okay, and we're going to label it. And then we're going to split it into 3. And then here we're going to have an X, and we're going to have a minus 1. Okay, so let's check to see what happens. Okay, in order for this to be a factor, what's going to happen is this last box, as we discovered before, this last bottom right box will have to match the -8. Let's see if that happens. Okay, so we know in the first box, we're going to have x to the third. What times x is equal to x to the third? Well, it must be x squared, right? X squared times -1 is -x squared. Okay. Now, but the polynomial itself has to add up to 5x squared. These two have to add up to 5x squared. So -x squared plus what is equal to 5x squared? -1 plus what is equal to 5? Well, it must be 6. 6x. And so squared. So that must be a 6x squared. Okay. What times x gives you 6x squared? 6x. Okay. 6x times -1, -6x. Okay. Now let's look at the next term. We've got a 2. -6x plus what is equal to 2x? Looks like that's going to be -6 plus what equals 2? 8. 8x. That's got to be 8. 8 times x is 8x. 8 times -1 is -8. Our last term is a -8. We have made it. Perfect. It works. So my polynomial is x squared plus 6x plus 8. Hey, guess what? That factors. You might recognize that as the factors. And what two numbers add to 6 and multiply to 8? It is 4 and 2. So the whole polynomial factors as x minus 1 times x plus 4 times x plus 2. Look at that. We just factored the whole thing. How fancy is that? Now that is some algebra right there. Okay, from that you could draw a graph. And at this point, you know exactly what that graph is going to look like. It's going to have x-intercepts of 1, -4, -2, and it's going to pass through those x's. It's going to look a little something like this. You're going to have a 1, you're going to have a -4, here's a -2. It's positive, so it's going to do this. It's going to start from the bottom. It's going to go 1, 2, 3. Kind of like that. Again, that is probably a very quick, rough sketch. But this is how division works. So in this particular case, really what we're doing is we're not actually dividing, is we're undoing multiplication. by figuring out what the terms have to be to get the multiplication to work and calling that division. So the only issue that we have was, as we discussed before, is if this last term does not match, you don't get a -8 in the bottom here. This does not match the constant term here, then you're kind of stuck. You have a remainder, but it's hard to visualize what that remainder is, what it is. And then on top of that, this process starts to get a little bit tougher when you start getting more complex factors than x minus 1. So while this is good, and it does work, we have some more generalized processes that can handle this. Okay. So how would we actually handle the division as division? How would we do that? Let's start by handling something that you probably did some time ago. Long division. Oh, goodness. I can hear you screaming already. Ah, yes. Your agony is my joy. Or something like that. Anyway, it's not that hard, right? Do you remember how to do long division? If not, here's how. You're trying to figure out, let's say you have the number 2772, and you want to divide by 11. So the first thing that you look at is you look at the first couple terms, right? Does 11 go into 2? No. Does 11 go into 27? Sure. It goes into 27 twice. 11 times 2 is 22. And that leaves us with 5. Does 11 go into 5? No, so we're going to drop down to 7. How many times does 11 go into 57? 5 times. 11 times 5 is, 55. And we're going to subtract the 55 off, and we get 2. Bring down the next 2. How many times does 11 go into 22? Twice. 11 times 2 is 22. Nothing left. Hey, so that's long division. And again, with this particular one, you don't get a remainder because the division works evenly. But this time, the remainder, if there was a remainder, it appears nicely at the bottom, which is kind of nice. So if you think about it, I want you to compare now how we looked at this versus how we looked at some of the previous problems. So notice that we figured out, we basically did 27 divided by 11, okay? What multiplied by 11 gives you 27? Or something kind of close to 27. And so that's 2. And then we figured out what the difference is. And we shift over a term. How many times does 11 go into 57? And we figure that out, figure out the difference, and then shift over. That's kind of what we did here. We figured out how many times x went into x squared, or sorry, x went into x to the third. And then we figured out, we did, we calculated the next term, x squared times -1. And then we looked at these two here and said, well, how far off are we from the true answer of 5x squared? And so we subtracted 5x squared minus -x squared. And that produces 6x squared. And now we shift over and we divide by x. And then we figure out the difference in the x's. And we shift over and we divide by x. And we shift over. So can you see how it can be kind of similar to this? So let's see what this might look like in a bit. We'll see what this looks like with an actual polynomial. Here we go. So here's an example of how this looks um, with a polynomial. Let's say we wanted to divide 2x to the third plus 7x squared plus 7x plus 2, and we want to divide by x plus 1. So in other words, going back to the original formulation, we want to know x plus 1 times what is going to get us 2x to the third plus 7x squared plus 7x plus 2. And by that, we're essentially want to divide by x plus 1. So 2x to the third, 7x squared, 7x 2, and we want to divide by x plus 1. And that's what this is going to do here. So let's see. So the first question is, okay, so we look at the first term, is we have 2x to the third, right? 2x to the third, the very first thing that we're going to do is we're going to divide by x. So step 1 is we're going to divide by the x term. Okay, so 2x to the third by x, and that's going to get us 2x squared. Now, I don't write it directly above the 2x to the third. I write it above the 7x squared. Why? Because that lines up the terms super nicely. Look at how all my like terms are all lined up. That is key to keeping this organized. So we divide first term by x term. Okay, of divisor. Okay, perfect. And that gets us 2x squared. Now, where does the next line come from? If you recall, in regular, oops, let's get rid of this page here. In this problem here, we then had to multiply that first digit of 2. We multiplied by 11, and that gets us the 22. So that's what I'm going to do here. 2x squared multiplied not just by x, but this time we're going to actually multiply by the whole x plus 1. Multiply by the whole divisor, and we're going to write that down. Okay, but now wait a minute. You might notice that the signs are different. 2x squared times x is not negative, it's positive 2x to the third. 2x squared times 1 is 2x squared. But then why are there minus signs here? It's because the next thing that you have to do is subtract. So when we subtract, now again, one common thing that you can do for subtracting is you can change and add. And so that's what's happening here. I change the signs and then I add. Negative 2x third plus 2x third cancels out. Gone. No term left. 7x squared minus 2x squared is 5x squared. Wonderful. Okay. So at that point, that's the same location as we had the 5 here. We subtracted these and we got the 5. Now, at that point, the division is no longer happening, so we bring the next term down and we continue. So that's what happens here. Step 4, drop next term and repeat. And so we drop the next term. But we repeat starting from 5x squared. What's 5x squared divided by x? 5x. 5x times x plus 1, 5x squared plus 5x. Change the signs and add. Cancels out. 7 plus negative 5 is 2. 7 minus 5 is 2. Drop down the 2. Now divide again. 2x divided by x is 2. Now multiply 2 by x plus 1, 2x plus 2. Change signs and add. And when that happens, all your terms disappear. And at the end, you're left with 0. That 0 is your remainder. That means the division worked out evenly. Fantastic. So that's an example of how it works. Now, let's actually look at a few examples where we do it out. Okay. So now really showing you the connection between this and the box, right? Okay. So let's say you have the expression 6x squared minus 7x minus 5. And let's say you had a factor of 2x plus 1. Maybe you knew that negative 1/2 is a solution. But anyway, he attempts to divide by 2x plus 1. And when you do the long division process, you'll see that it works out evenly. Now, what happens if we use the box? Again, we're going to see the connection here. Okay, so 2x times what gives you 6x squared? 3x, right? 3x times 1 is 3x. 6x squared plus 3x. But again, notice the minus signs, right? We change them to minus, we add, right? So we've got a minus 7x. So what is minus 7x minus 3x? A minus 10x. And because negative 10 plus 3 is negative 7. Now that must mean that what times 2x gives you this must be 5. Because 2 times negative 5 is negative 10. Okay? And then finally, negative 5 times 1 is negative 5. And since the negative 5's match, no remainder. So that's how it works. And you see how the numbers are very similar that you get. You get the 3x, you get the negative 10x in the problem. The difference is long division, this process in the green, is much more friendly to larger polynomials and becomes more of a direct process, where the box is kind of indirect, where we're undoing the multiplication rather than like actually performing division. Okay. Here's another one. Let's finish it. So in this particular case, we have the polynomial 2x to the third minus 7x squared plus x plus 10. Okay. So the first thing that happens, step 1, is there's a divide step. And we're going to divide the 2x to the third by the first x. That gets us 2x squared. Now 2x squared, the next step is to multiply by divisor. And so 2x squared times x minus 2, that's 2x to the third minus 4x squared. But the third step is we do a subtraction. When we subtract, the easiest way in this case to subtract is to just change the signs and add. So 2 plus negative 2 cancels out. Negative 7, now this was a minus 4 because 2 times negative 2 is minus 4. But we changed to addition and we're going to add. What's negative 7x squared plus 4x squared? It's negative 3x squared. Step 4, drop next, repeat. We're going to drop the next term. So now we're going to go back to the first step and we're going to divide, but it's not the first term of the polynomial. We're going to divide what we have at the bottom here. What is negative 3x squared divided by x? It's going to drop down to minus 3x. Multiply by the divisor, and that gets us negative 3x squared times negative 2. So negative 3 times negative 2 is positive 6x. Subtract. Or change signs and add. That cancels. X plus negative 6x is negative 5x. Drop the next term down. Now repeat. Now we're going to take this term, we're going to divide by x. And so we divide by x, and so that is minus 5. Negative 5 times x, negative 5x. Negative 5 times negative 2 is positive 10. We get the same thing. So when I change the signs, I get a 0. And once again, lucky enough, no remainder. While we're learning it, I tend to do problems without a remainder at first, just to make sure that you see all the numbers working. Then we can start worrying about remainders. Okay. Let's do the same thing. This time, let's start all the way from the beginning. And again, you'll see the connection with where we came up with the box. So let's say we figured out using our little box method that if we had 2x to the third plus 13x squared plus 16x plus 5, let's say we use it to figure out to divide by 2x plus 1. Well, let's see how that looks in long division. 2x to the third plus 13x squared plus 16x plus 5. I'm going to draw a big bar, like we did before, and I'm going to write 2x plus 1 on the outside. Okay, so first step. So again, let's write the steps up here. Divide, multiply, subtract, drop, repeat. Okay, so divide the first terms, 2x to the third divided by 2x. That's going to be 1x squared. Or just x squared. Okay, now we're going to multiply x squared times 2x, 2x to the third. Those first terms should always match because you want those first terms to cancel. X squared times 1 is just x squared. Okay, change the signs and add. Cancels. 13 plus negative 1 is 12x squared. And look, that's where the 12x squared comes from. You see it there. Okay? But this time we're doing it more directly rather than thinking about what actually multiplies. Okay, drop the next term. 10x plus 6x is 16x, right? So we have to figure out how to split the 10 and 6 apart. So what is 12x squared divided by 2x? Well, 12 divided by 2 is 6. So this is going to be 6x. 6x times 2x is, again, 12x squared. And 6x times 1 is 6x. Change the signs and add. There's our 10x. There's our 6 and our 10. Beautiful. Drop down the 5. 10x divided by 2x, 5. 5 times 2x, 10x. 5 times 1. Change the signs. And we're good. X squared plus 6x plus 5. Yes, that factors even farther, but we're not concerned with that at the second. Okay? But hey, the long division works. Okay. Now, for the sake of time here, this video is going to get a little bit long. We're already about a little bit past the 45-minute mark, which is about as long as a single class, right? So instead, we'll pick one of these. You know what? Let's do the first one because of the big number here. I like dealing with the bigger numbers. Both of these should be work out evenly. In fact, it does say that with known factors. So if done correctly, you should get a remainder of 0. Okay? All right. So let's tackle it. Let's write it down. We have x to the third minus 7x squared minus 16x plus 112. Okay. And we're going to divide by x minus 7. All right. So remember, divide, multiply, subtract, drop, repeat. So x to the third divided by x. That's x squared. But I put it above the x squared term. Again, let's keep our like terms lined up. Multiply x squared times this. X squared times minus 7 is minus 7x squared. Okay, now something interesting is going to happen. I'm glad I did this problem because this is going to sometimes happen. You're going to change the signs. And when you add them together, you're going to get a 0, not just for here, but you're also going to get a 0 for this one as well. If both terms drop or 0 out, then drop next 2 terms. Because if you drop a single term, there's still no need. You're going to have a minus 16x. Okay? You'll have a 0 here, and you could divide 0 by x, but that will just be 0. So instead, it's worthwhile to drop not just the one term, but the second term as well. And the other thing is, if you try to divide with just the one term, yeah, you're going to get a minus 16. Okay? You're going to get the minus 16, but the problem is you're going to get this 112, and it's not going to have anything to combine with. So you're going to have to bring the next term 2 terms down anyway. So we're going to bring 2 terms down. That way, negative 16 times x is negative 16x. And then 16 times 7 is 112. You can check that with a calculator. Positive 112, because negative times negative is positive. Change the signs. And they add up. Okay. And so you get x minus 7 times x squared minus 16. So from that in mind, actually x squared minus 16 factors farther, x minus 4, x plus 4. because it's a difference of squares. So this actually has three x-intercepts. It's got x-intercepts at 7, also at 4, and at -4. Okay. And I'll leave the next one just to shorten up the video a little bit. We have one good example that's on there. Okay. But looking at the next one shouldn't be terribly difficult. Looks like it's going to end up ending at a 5 because 15 divided by 3 is 5. Um, but you can go ahead and try that one out. I'm trying to see if I can quickly come up with an answer um, in my head. It doesn't look like I can. I'm trying to think of what that might be without having to do the whole long division out. Um, it's going to have an x squared. It's going to have a 5. So this is going to be, so it's going to be x squared times x plus 3. So it's going to be something that's a negative. You're going to have a big negative term here. So you are going to have um, 5x. And so what have you got? A minus 13x there? So I'm thinking you're going to have like a minus 6x there. So I would go ahead and bet that that's going to be, um, if you wanted to do this one out without having to actually go ahead and do it, your quotient, in other words, the remainder of, or the answer that you get should be x, oops, I don't know what happened there. I think it's just my thumb slipped. Should be, whoa, hello. Okay, should be x squared minus 6x plus 5. Okay, and um, yeah, actually, I'm looking at it, and that is in fact correct. Okay, so the quotient should be x squared minus 6x plus 5. And you can check that out yourself. Okay, last but not least, here's one final thing. Unfortunately, when you do long division, it is a fairly lengthy process, right? And unfortunately, when you have such a lengthy process, it's very easy, as you can see with all the different operations that are going on, it's very easy to make a math error. So here's an example of a person who did the division, attempted to divide by x plus 11, um, and x plus 11 is a factor. So the remainder should be 0. But they don't get 0. They get 2156 at the bottom. Ew. That's yucky. The remainders don't usually get that high, right? Now, here's the thing. Just because you have an x plus 11 doesn't necessarily mean that the remainder has to be under 11, like it would for regular division. Because of the presence of the x, and x can be any number, your remainders could literally be anything. So this, for some problems, this could be correct. But here, um, it is not. Let's see where the error might be. Okay, so x to the third divided by x is x squared, and x squared uh, times x plus 11 negative x to, and to, oh, x squared times 11 is 11x squared. But they were supposed to change the sign here. So what you should have is not a 21. You get the 11x squared. So x squared, x to the third, 11x squared. They forgot to change the sign on the 11. That's what happened. And so you actually should be ending up with a negative x squared. Okay. That was the mistake that they made. And judging from that, it looks like they, um, 21 times 11, 21 times 11, they um, continued to make that mistake all the way through. They did it with this term as well. They forgot to change the sign here. So they actually did that consistently through the whole problem. They did never change the sign of the second number. Okay, so let's do this out correctly. What's negative x squared divided by x? That is minus x. And we multiply that, we get a minus x squared minus 11x. Change the signs and add negative 23. Now we're going to go backwards from 11, so that's 12. So negative 12x minus 132. Okay, so negative 12 divided by x, that's minus 12. And so negative 12 times x is negative 12x. Negative 12 times 11 is negative 132. Change the signs, and now it works. And finally, write p of x as the product of two factors. P of x is equal to x plus 11 times x squared minus x minus 12. But it's also equal to x plus 11 times x minus 4 times x plus 3. Simply because that last part factors. Now, a lot of them have been factoring, but do they have to factor? No, they don't. This doesn't have to be factorable, because for some of these, they are. And that allows us to make a pretty quick graph. Well, there you go. That's polynomial long division for you. I hope that wasn't too confusing, but we're going to take some time and practice this in class. Once you get used to the process, it's not that bad. Very kind of disciplined in your addition, subtraction, and multiplication. Okay? Have fun with this. Work on some of the practice problems that we do, and hopefully it works out. Take care.